Okay, so our next talk is by Smale, and the title is Topology and Geometry of Manifolds from Sample.
Thank you, Bologna. And so, with respect to Partha, let me just say that he was my best friend in Chicago for the 7 years that I spent here before I went to Hodge. And we did many things together. For example, we put together in these few years that I was here 3 conferences held in Chicago. The last was a big conference organized with Misha Belkin. And we had together over $2 million grant from the NSF, which we administered during this time. We wrote 2 papers with Smale. Smale talked about them yesterday. And so I miss Partha very much. Now, what I want to talk about today are problems coming out of Partha's work in maybe 2 closely related areas. One is topology of manifolds, finding the topology or finding the homology of manifolds. This is an area that Smale and Partha and I worked on for many years. And in fact, the last of the 2 papers, I think, is maybe just published or just coming out. I'm not sure. And the other related work of Partha was joint with Misha Belkin, and that has to do more with the Laplacian on a manifold and various computational aspects, the graph Laplacian. So I want to talk about some developments that I've been connected with, which give some perspective on extending those problems. For example, the problem that I worked on with Partha and Misha of finding the homology groups of a manifold, that a lot of people complain about with some good reason. Most data doesn't come in a manifold. So a big problem is to, on a more general setting than a manifold, have some kind of corresponding theory where one computes the corresponding homology groups through data, through a sample. Okay, so that's one problem I'd like to address today. And another problem has to do with the work with Misha on the Laplacian on graphs and Laplacian on manifolds. So what I would like to talk about today also addresses extension of that problem to the higher order Laplacians. The higher order Laplacians which appear in classical Hodge theory. And so those are problems that are mixed up together. And their extensions that I'm talking about are also mixed together in this area of Hodge theory. So this is something I've been working a lot with my son, Nat Smale. And then joined us, but for the moment, I'll speak especially of what Nat and I did, starting 4 years ago. Hodge theory itself, due to Hodge, came out in the 30s, deals with smooth manifolds and geometry of smooth manifolds. And I see myself, the goal of Hodge theory is to find in each homology class on a smooth manifold, or cohomology class. One is optimal, which is optimal in the sense of geometry. So the geometry allows one to choose in each homology class a unique optimal class. And so this has got some various implications because the optimal geometric one is much more likely to be of use in various situations, for example, physics and other areas. In this Hodge theory of Hodge on differentiable manifolds led Nat and me to investigate something, a Hodge theory, which did not necessarily apply to manifolds, apply to a more general situation. And so we worked, let me write this on a space X, which is a measure space, and a metric distance function. So here we have a distance function and a measure with various regularity properties. And we do Hodge theory for this. That was the goal. And there's a scale, a fixed scale alpha, which we look at. This is connected a little bit with persistence homology, but we work with a fixed scale, not a variable scale. Okay, so these are the ingredients for Hodge theory, and certainly, if this were simply successful, then this would give us a way of having an extension of homology computation in quite general spaces. But as we'll see, in this setting are easier proposed than solved. And I'll try to give the perspective on this situation. So this deals with the two angles. One is higher order Laplacian, and the other angle extending the finding of homology to more general spaces than manifolds. Okay, so maybe it's good to start with by defining a main invariant. This is a key invariant which we deal with. This is a homology group. I'll write it alpha because it depends on a fixed scale. It's going to be L2. L2 doesn't make things too easy because functions aren't even defined pointwise on the space X at degree L. So I want to define this space. Okay, so this is key to our development. And even more key, I'll define this momentarily, even more key is that this has finite dimension. Okay? This is what we'll call hypothesis 1. It's the main hypothesis for everything I talk about, that this have finite dimensional, this L2 homology. Okay, so the definition of the homology goes as follows. We take these spaces L2 of a neighborhood I'll describe momentarily of the diagonal, the alpha neighborhood of the diagonal. And I want to map that into L2 UL plus 1. So this is the subtle part. Not too subtle, but maybe it takes a little bit if you're not used to digest this. This is going to be inspired a little bit by what's called Alexander Spanier homology. So I want to define a map boundary here for every L. Sometimes we might call this coboundary L. Usually I'll just drop the X. So let me define coboundary. Coboundary of F, take a function in here. Let me, I got to say what UL alpha is. This is the neighborhood of the diagonal as follows. UL alpha of X is equal to the set of all X L times belonging to X cross x L times L-fold product, the L, which satisfy the distance of xi to the diagonal in the space should be less than alpha, less than or equal. Okay, so this is the neighborhood of the diagonal. This is for all I. Any questions on that? You think of this as the neighborhood of the diagonal. That's defined precisely by that. I think I have that right. Okay. And it can be checked that this map co-boundary, if I take f in here, so f is a function on space exactly. Now I want to say co-boundary of f at a point x0, xl equals. See, co-boundary of f is going to be a function on L plus 1 variables, neighborhood of the diagonal. And this is defined, this is the definition, minus 1 to the I f of x0, xi omitted up to xl. If you think about it for a minute, this does make sense because f is defined on all variables. Co-boundary f is defined on L plus 1 variables. We take this alternating sum where we omit the ith x. Okay, so far okay? So if you haven't seen this before, maybe it's hard to fathom all this. And then one can prove that this is zero. Zero. Co-boundary composed with itself is 0. Another co-boundary. And then we can write this group H alpha L2 L is equal to the kernel. This is a standard construction in topology and homology divided by the image of co-boundary. So this is going to be kernel of, this would be L plus 1, kernel of co-boundary L plus 1 divided by the image L. So these are all real-valued functions, real-valued cohomology. This is a real-valued cohomology group. And so this is going to be a basic ingredient of what we do. And this group here, vector spaces, in fact, is over the reals. Everything's a vector space. Okay? Don't hesitate to stop me if you have some question or otherwise. And so this is going to be our central problem, hypothesis. Here is two amazing facts. Not amazing, but well, they're amazing to us for a while. Hypothesis 1, here's the theorem. And let me call this the soft theorem. The soft theorem asserts hypothesis 1, the finiteness here, implies Hodge theory. Okay, that's soft. And Nat and I proved that early in the development. Hard theorem is to say when his hypothesis is true. And here is the, see, we can see from the soft theorem that it's very nice if we can check the hypothesis. Because I'll explain what the Hodge theory is presently, but it gives a huge amount of structure, the identifications of the homology and everything else. It's a pretty strong result. The hard theorem gives us conditions for which this is true. We need the hard theorem to apply the soft theorem. Now, here's the trouble with the hard theorem. We found it, and I think it is extremely difficult to find any spaces X where this is true. But also, it's very, very difficult to find any spaces for which it's false. And it took us a long time with many people answering those questions. Yeah, that's why I call this hard. Because it's very hard to know, even to find any kind of spaces, or there's some trivial cases where it's true if X is a finite space. If X is a finite space, then it's true, and it's trivial to prove. Otherwise, besides those finite spaces, it's pretty much impossible, very hard to find what's true. And finding a counterexample, well, we were 6 months before, or a year before we even, it was suggested there might be a counterexample. Okay? So let me give a little history before I explain Hodge theory. Hodge theory won't be any big surprises. But so I'll just hold off because I don't have too much room. But history is as follows. So we wrote up a paper. Well, here, let me write hypothesis 0. And that is coboundary has closed image. So hypothesis 1 is easy to see, implies hypothesis 0. Coboundary is a closed image. I think the converse I'm pretty sure is not true. Okay, so what we actually proved, Nat and I, even with this hypothesis 0, we still get a Hodge theory. Okay, these things by now, after the 4 years, are finished processing with the journal and will appear pretty soon in the Journal of FOCM, Foundations of Computational Math, and quite a long paper. Okay, so our first version of our paper was that hypothesis 0 was always true. The X should be compact metric. So that was the first version of our paper. And then Thomas Schick had some doubts, and he eventually found a counterexample. It's in our paper now, it's Appendix A. He has a counterexample where you do not have a closed image, hence you don't have this hypothesis. Okay, so then hypothesis 0 counterexample implies a counterexample for hypothesis, if I'm not mistaken. Right. Okay. Yeah, so it's a hard counterexample to really understand. I think practically it's all written out in rigorous detail, but it's a countable set in an infinite dimensional Banach space. And it's hard to get your hands on it. You know, I spent a lot of time on it. We had a seminar on it in Hong Kong, and you know, I think people that might have understood it have probably forgotten what it means now. It would be good if it were more conceptualized. Okay, so then Schick joined up with Bertoldi, Laurent Bertoldi. These are both at Göttingen. And what they did was to produce a result of the hard theorem. That, in fact, if you take a Riemannian manifold with small alpha, then this is finite. But that was wrong. Nat and I found a mistake in that. And eventually, mainly Nat and I did produce a theorem which so far looks good to that effect. So the hard theorem would assert that hypothesis 1, finite dimension, implies, where are we? Implies, no, Riemannian manifold compact and alpha small enough, and we say exactly how small, implies hypothesis 1. So that means we do have a Hodge theory for the most classical case of a manifold with small alpha. Okay, I still haven't said the Hodge theory, but I will. So this was a hard proof. But let me just go ahead a little bit, because partly I'm here just to tell the story of these things. The papers are all finished. You can find them either on my website, and some theorem paper with Nat Smale's web, or write Nat Smale for one of the papers. So about 3 weeks ago, this is Nat's theorem. And this is motivated by the fact here we have this, but we're not really ahead of what we did with Partha and Smale. Here we have the situation which implicitly allows us, or explicitly soon enough, to compute the homology. And it's the ordinary homology, but we already had some good method. So it's so exciting just to find another way of doing that. Well, it's a little exciting, but still not good enough. It doesn't deal with this problem of extending the manifold theory to non-manifolds. Okay, so Nat theorem 3 weeks ago asserts also Alexandrov spaces. And here he has a condition on the curvature being bounded above. So this is what Nat proved. So here we have spaces which contain manifolds with boundary, for example. That's something we hadn't known before in any of this work. Also includes classes of singular spaces. Alexandrov space, which I'm not even prepared to define it here, is a space where you have a notion of geodesic for small distances. And the geodesics during 2 points exist in a reasonable sense. And they have still another condition. And Alexandrov spaces, they have to be careful. Not F, don't write 2 F's here. If you have 2 F's here, then you get a completely different definition of Alexandrov spaces. Alexandrov with F refers to Paul Alexandrov, and this is A Alexandrov here. Now, these are much more, have a lot greater depth than those of Paul Alexandrov. And in fact, they were used by Partha in this proof of Poincare conjecture, dimension 3. And so it's hard to get one's hands on here, but there are theorems due to Alexandrov even and others. They include these some class of singular spaces called Pitts buildings, folds with boundary, other things. So anyway, this certainly contains interesting spaces that go beyond here. And another description of these spaces, you take ordinary Riemannian manifolds and certain limits under Gromov-Hausdorff distance to get the Alexandrov spaces. Okay? So this is just giving a sort of a rundown of the picture here. So let me then erase some of the stuff at the top and write down the oops, maybe I should leave this for just a minute. Let me write down the Hodge theory, Hodge theorem. Okay, so here we have this co-boundary, which I've partly erased, L2 alpha. These are Hilbert spaces with that measure. And so we can take the adjoint. Maybe I forgot to mention, this is a bounded operator. We proved that, Nat and I proved it early. That's a bounded operator. We have an adjoint, another bounded operator. So we can write now the composition, this going from here to here is a map of space into itself. These are what we call L-1 forms. These ones. Okay, then we can also do the following. We can come up from the previous level, come up previous level, and then take the adjoint, and then come back again by co-boundary. So that would be co-boundary star. Or am I doing this the wrong direction maybe? So this one was first co-boundary followed by co-boundary star that I just mentioned. And now we write co-boundary star. Co-boundary star. That's our version of the Hodge Laplacian, L-1, scaled by alpha. It's a map of this space into itself. Bounded operator. Okay, so once we have a Laplacian, then we just, different from the classical Laplacian. It doesn't use differentiation, which in some ways is a lot better. An integral operator. Okay, so then the Laplacian says that if we look at H, is homology. Let me go back to index L, alpha. Let me just take L2, UL plus 1 alpha is equal to a direct sum of the image of co-boundary plus image boundary star plus kernel of the Laplacian, L. You have to put the right indices here, L plus 1, or whatever. So that's what the Hodge theorem says. These are all closed subspaces, and this is a direct sum, Hilbert space sense, to this space here. And
this last statement is classical Hodge theory?
no, that's our Hodge theory.
Okay.
Because this is our Hodge Laplacian here. So this should be L, and this would be alpha. Yeah, this is our Hodge theory. And moreover, kernel of this Hodge Laplacian is isomorphic, naturally enough, to this group I just mentioned, HL, HL of X alpha L2. This one that comes into hypothesis 1. So this is the Hodge theory, the Hodge decomposition. So this connects both the classical Hodge theory of Hodge and this interprets these harmonic functions. These are harmonic functions of order L. We call them alpha harmonic functions because they're not exactly but closely related to the classical Hodge harmonic functions. The mention of the space of harmonic functions forms is the same as the dimension of the homology. And so this gives this geometric realization of every homology class by something very geometrical, because these harmonic forms are given by, if you want, an optimization problem, or a integral operator problem, in our case, a differential operator problem in the classical case. So we replace the differential operator with an integral operator, bounded operator. So in that sense, it's easier than the classical Hodge theory. And then I think now I've explained this. Okay. No questions, anybody? Huh?
What's the role of the measure?
Well, you can't do much without the measure, because that defines.
But if you say you have mutually continuous measures with respect to each other, do you get the same groups?
Probably, but one has to be a little careful about those things. I don't think we used, see, we don't use much properties of the measure except to be Borel, and they're all, in this setting, alpha small on the manifold, then things are easier and one can give better answers, because they're all, these will be isomorphic. Moreover, this is now for a manifold. Yes, for a manifold, we can say more. In small alpha, then H alpha equals H classic. Yeah, so if you're on a manifold case, things are very clear in that respect. So we recover the usual homology in these theorems, in the hard theorems.
Is there a way of comparing or relating what happens when you change alpha? Like, are there inclusion maps?
Yeah, so something we couldn't do for years, but now we have this these theorems. We can do that for small alpha. Then if you change small alpha, everything's an isomorphism. What?
So some threshold on the alpha, and then once you pass that threshold, is there a way of relating it, even if the homology of X?
Yeah,
Something else?
you still relate it. Well, we have to be careful. For this Riemannian manifold case, we can change alpha as long as it's small, and everything's an isomorphism. Then you have canonical maps between the different alpha. And in general, you get a canonical map if you reduce alpha. But it's not isomorphism in general. And in this case here, Alexandrov spaces, we don't know that they're always the same as the ordinary cohomology of the space, because if you take spaces where you have bad local connectedness properties, then you'll have trouble with your question. And I don't know if these have good local connectedness properties, maybe not.
And they're also compact.
Everything's compact here, yeah. Oh yeah, all these spaces are compact. Okay. Any other questions on that? All right. So let me look then at. I can give some. It's nice when I can talk about things I discovered yesterday, but this isn't. I won't quite say it's a discovery, but I had lunch yesterday with Misha and Lorenzo, and we discussed a lot this question I raised with them, which seems to be okay, but so we have to see. And it's the following. If we look at this work of Misha and Partha on the Laplacian, what they did was to show, this is now Misha and Partha through the last 8 years or so the following theorem. And that is, if we look at the Laplacian, this is now the 0th Laplacian. This is classic. Well, it's Hodge theory degree 0. It's just ordinary Laplacian here. What they've done is to compare the following. They look at this Laplacian on a manifold M, Riemannian compact, and also the graph Laplacian. Let me say x bar is data. I'll use my own notation, and I may not do exactly the same form they have it. But if we have a finite set of points, then one can also define the graph Laplacian according to an associated graph to the finite set of points, and then therefore the graph Laplacian. So the graph Laplacian, one can compute. One can compute everything about that. And the question is, as x bar grows and grows by random draws, does that converge to that? And so their results are on that subject. But there are different notions of convergence. Pointwise convergence, more spectral convergence. In the last result, stronger, and that paper, Misha says, will be finished in a few weeks. So they've been doing that a long time, but this paper with Partha is on the last paper is on the hardest type of convergence of this to this. The graph Laplacian to the Laplacian, the manifold with respect to spectrum. I hope I'm fair to you, Misha. Because okay, some versions published. Okay. Yeah. All right. Okay. Okay. So this goes through the following. You first go through an integral operator, like the heat kernel goes through a, let me just say integral operator, heat equation. And then this goes into this. So it's a two-stage process that they use. One is to go from a sample to an integral operator, and then the other is to go from the integral operator to the Laplacian. Okay. So this is a great thing they did. And you can ask similar questions everywhere I'm talking about here. Those questions are all questions in the setting. So what I asked Lorenzo and Misha yesterday was to take our Laplacian at scale alpha. We have a formula for this in our paper. By the way, as I said, all these things that are done are in my website. So this is a paper for 4 people, and we have a formula for Laplacian on a function f. It's not a bad formula, no derivatives. Well, it can't be derivatives because they're on these spaces where it makes sense. So this formula is very general, just on a metric space, compact metric space with a probability measure. Then this is given by, I have it in my paper right there, integral, and so on. Okay, so you can write down this formula, and now we can see and this formula, of course, is going to have some x1 up x0, and over here is some x0, so some f here too. Now the same form, and this is one advantage of our approach here, the same formula is valid for x bar as it is for any x. So that the formula suggests, why not just let x bar be taken from a bigger and bigger draw from the probability measure, and we should get what's going on here. So that's the question I discussed with them. And I know that in L2, there's our problems because then we don't go from a function on L2 to a function on x bar, because a function on L2 is not pointwise defined. So that's a problem. So what I suggested is we work with continuous functions. Continuous functions, L plus 1, say, and UL plus 1. And so this makes very good sense, this Laplacian. And this formula makes good sense, and it's continuous, clearly continuous. So now, with a continuous function, then we can restrict f in all these functions to x bar, and we get a nice canonical map. And so now, with that picture, looks, all that I can say is that they were encouraging at this lunch yesterday that if we take x bar larger and larger, we get some kind of convergence in probability for x, for this way, x bar alpha to x alpha. And so this is maybe point-wise that would be easier to prove, and it might be in some stronger sense, maybe some operator type close to operator or some uniformity. It seems like it probably has some uniformity to it. Okay, so that gives us then a way of almost skipping one of these steps, because we could go directly from this finite dimensional Laplacian, higher order Laplacian, to be computed pretty easily to the Laplacian on our space and get consistency. That's the idea. And then we could use the algorithm. So let's just take e to the minus t Laplacian x bar alpha. Use this kind of algorithm, converge to something in the kernel of the Laplacian. So this would be a fairly direct way of computing things. So this again is partly inspired by the work I did with Partha and Smale on finding homology of manifolds, and so this would give a way of doing that somewhat different way, this construction, and it seems to me it's a good chance. Things have to be worked out, and one has that this could give an alternate way of finding homology of a manifold from random data. This is what we did. And this is a suggested alternate way.
This random data would have to come directly from it. Like, how would that work with noise?
Well, yeah, that's maybe not quite ready to worry about until a little more of this is solidified. In principle, I would guess that this is intrinsic methods. Don't worry at the moment. These can be done intrinsically on an intrinsic manifold. So noise on an intrinsic manifold isn't quite so serious as when you're embedded in Euclidean space, but still you can ask about noise. I wouldn't worry about it too much, especially at this point. Yeah. Okay. Well, I think it might be in the last minutes just to give an example of what's going on here. There's, truthfully, more things I could add. What does one of these look like? Let me give an example of a harmonic form in our sense, an alpha harmonic form. Okay, let's do. I do it on a sphere. So here I want a function. See, this is not your differential form in the classical sense at all. This is a function of 3 variables. And we pass pretty early to alternating functions. It makes more sense to work with alternating functions. That if you permute the xi's by an alternation, you just change the sign accordingly like this. Okay, so I want to define this to be an example where this is harmonic, a 2-sphere. I take these 3 points, x0, x1, and over here is x2. 3 points, and say alpha is small enough so these are in the same hemisphere. These 3 points in the same hemisphere, and I want to describe the two-dimensional form. This is the highest dimensional form, and it's unique because the homology of this is one-dimensional. So what I do is I take this geodesic triangle, and I take the volume, appropriately signed with sign. That defines a harmonic function. That's in our first paper. Okay, and the second paper, yeah, so this works for any manifolds of constant curvature construction. And the second paper Pat and I wrote is the following. It relates this homology, these objects here, these operators. So these are quite different than the classical operators on a manifold. These are functions on one variable. So what we do is to connect those up. So this is a paper on my website by the two of us, finished earlier this year. And what we do is we look at Laplacian alpha. This goes from L2 UL plus 1 L into itself. And also we have the classical Laplacian. This belongs to this space of sections, lambda L, on a manifold. So these are one forms on the manifold if you want. Or if you want, there are sections of the dual of the tangent bundle, smooth sections. These are the one form. These are L differential forms on the manifold. Exterior differential forms. I'm not going to define them now. But we want to define a map from omega L, this space lambda L, to here, and we'll just put the C infinity for the moment. So we want to define maps both ways. And so we have a map C going one way and phi going the other way. We define it in our paper. And we show both of those are chain maps. So they commute with our co-boundary that I've been writing down all the time and the exterior derivative of the manifold. So they commute, both of these are chain maps. And one is the inverse to the other. You can tell which is which pretty quick. I think it's what? Phi followed by C. All these are indexed by L equals the identity. Yeah. For small alpha. So we do that. And that it's good to have these isomorphisms. Because this is, I think, another important question I haven't addressed, but we would like to see more clearly how the classical Hodge theory here works to our Hodge theory here. And what we prove directly in this is that the Deram theory is defined on here. Classical Deram cohomology is defined in terms of exterior derivative, and these chain maps, these properties, also this hard theorem over here allows us to say that's going to be an isomorphism with our cohomology up here. So the Deram is exactly the same, defined by forms or defined by our coboundary. And let me just say the hard theorem goes through some rather tough topological geometric constructions and eventually uses a bicomplex argument, like a spectral sequence argument in algebraic topology. Okay, well, thanks very much.